6.8 Partial Pressure, Dalton's Law. The partial pressure of a gas is the pressure that each gas in a mixture would exert if it were by itself in the container. So the picture to help you understand this. So let's say that we had some pressure of helium that exerted in this cylinder 2 atmosphere pressure. And we had another cylinder of argon that exerted 4 atmospheric pressure. Well, if we were to combine these two in the same size of cylinder, that the pressure total would be the pressure of the helium plus the pressure of the argon. So the overall pressure would be 6 atmospheres. So you'll notice that the Dalton's law of partial pressures indicates that the pressure depends on the total number of gas particles, not the types of particles, and that the pressure exerted by the gases in the mixture is the sum of all of those different pressures of those gases. For example, at STP, a mole of pure gas in a volume of 22.4 liters would exert the same pressure as 1 mole of a gas mixture in 22.4 liters. So it doesn't matter the type of gas, that you still add the moles up for that pressure. Example of using gases and pressure and the different kinds of gases is scuba diving. If you've done any scuba diving, then you have done a fair amount of learning of how you need to make sure that you don't dive too deep, or that your mixture is correct depending on your type of diving, or that you don't rise up too fast so that you won't get the bends. But when you're diving, the increased pressure causes nitrogen to dissolve in the blood. Why? Because you're breathing it in, and as more pressure is pushing on it, then you're going to get more nitrogen in your blood. Well, one problem with that is if you get too deep, then if you have more nitrogen in your blood and you've got a bunch of blood vessels in your brain, it kind of leads to symptoms of as if you're drunken, and which means you don't always make the right choices. So you got to be careful on that. But then usually you just don't go too deep. But another issue is that once you've gone down, you have all these nitrogen bubbles in your blood, and if you come up too fast, then they're going to come out of your blood vessels, and you have a whole bunch of blood vessels in your brain, and then the oxygen would come out of that. That wouldn't be good. Or in your joints, that's why the stiffness. It's also why they say don't go for a plane ride like as soon as you've got through diving. You've got to give yourself X amount of time before you get in a plane where it's decreased pressure. And you actually got to calculate, okay, I've been down diving for X amount of time. I've got to make sure that I give my body X amount of time to get that extra nitrogen out so issues don't happen. So air is a gas mixture. The air we breathe, yes, it is a gas mixture, and it contains mostly nitrogen and oxygen with other amounts of small gases, some carbon dioxide, some argon, a little bit of water gas. Now, in our lungs, the oxygen enters into the blood while the carbon dioxide from the blood is released. In the tissues, the oxygen enters the cells, which releases the CO2 into the blood. And this is how we are going to get rid of our CO2, is we got to make sure we're breathing. And how does that happen? In the body, the O2 flows into the tissues because the partial pressure of the O2 is higher in the blood and lower in the tissues. The carbon dioxide flows out of the tissues because the partial pressure of the CO2 is higher in the tissues and lower in the blood. Notice these different, this chart with the different partial pressures of the O2 and the CO2. Now, while we're breathing, notice the total pressures is our atmospheric pressure, the 760 millimeters mercury. And depending on if we're breathing in or breathing out, then we're going to have a different pressure of these different gases. So you can see the exact numbers here, for example, which thank goodness we're going to be able to breathe out a lot more of our carbon dioxide. Notice 68 millimeters mercury compared to the 0.3 that's coming in. Now, what's interesting, I don't know if you've ever needed to be treated at a wound center, but in the hypobaric chamber, oxygen can be delivered 2 to 3 times greater than at normal atmospheric pressure. And the reason why is that because it can help fight bacterial infections. A person undergoing treatment in the hypobaric chamber must undergo decompression, though, when you finish up, so that the oxygen that's dissolved in your bloodstream doesn't form bubbles in the circulatory system. Now, as a whole, the math, the calculations in this section will not be in your sapling homework or on the test. This is just lots of real-life examples.